thing recorded. I've got a new web camera today. I'm so excited. Let's pin me. So you let me know out there in the land if you need anything. I have you in my ear. My other Bluetooth is not working though, so hopefully you hear me okay. And let's hope this works. So I've got lots of things plugged in all at the same time. That is going to be really frustrating if that does not work. So what I'll do, no, let's do this. Let's just hope. Yay. Okay. If you're at home, make sure you take your attendance on Infinite Campus. You don't have to drop your name in the chat. Just make sure you do that. And let's take out that homework 2.2a. All right, 4.5. (2.2a) solutions. Okay, so I'd like to go through this slowly to make sure that we've got it, because kind of from here we really get into like a level where I am trusting that you know how to do it, so we can go to higher degree stuff. So take a look. So part one was just find the x-intercepts, and there's lots of different ways to do it based on the kind of question that you've got potentially. And with the first one, because there's only one x in the problem, when I said equal to 0, just solve it, right? Add 7, divide by 4, take the square root, square root of the top, square root of the bottom. So square root of 7 is the square root of 7, but the square root of 4 is 2. The denominator is rationalized, so we know we're good. We don't have to do anything else. We throw the plus or minus out in front. Okay. With number 2, I did it both ways because it's not factorable. And I hope that you try that first. I always want to try to see if things are factorable, because if they are, hold on, I got to share my screen. I forgot. There we go. So there at the top, folks at home, you can see the answer for number 1. But there is 2. If it's not factorable, because there's no 2 numbers that add to 4 multiply to -6, not nice ones anyway, and those are the ones we're looking for. You can do it one way or the other. Okay, so make sure you got to either you work through either version. You don't have to do both. Just pick one that you like. And I mean, the reality of this is that when you get to the test in, I don't know, a week or 2, you'll have already found the vertex and written in vertex form, in part C and part D of this question. And so vertex form might already be kind of halfway done at that point. So maybe you go with the one on the right, but maybe you're like, I know how to do the quadratic formula. It works. I can do it. Is that a question? I love questions. What's up, Daryl? Sure. Shoot. Number 2. The square root of 40. Okay. So simplifying radicals. Super, super nice idea to make my numbers smaller and simpler. Okay. Is the square root of 40 perfect? Plug it in the calculator to get a nice number? No, which means it's irrational, but there might be a better version of that answer. And so when I take, how should I say this? When I take the square root of 2 numbers and multiply them together, I can just put them under the square root. Like this is the square root of those 2 numbers being multiplied together, and I can get myself to there. So what 2 numbers multiply to 40? Well, 1 and 40, 2 and 20, 4 and 10, 8 and 5, and then it wraps back around 10 and 4 and goes that way. So are any of those combinations, do any of those combinations have a perfect square in them? 1 times 40, obviously not. 2 times 20, 4 times 10. What's the square root of 4? Exactly 2, right? I don't need the square root anymore. So that's how that worked out. That if you can break apart your imperfect square root into the product of two where one of them's nice, then you can simplify just that one. And what that allowed me to do is take 2/6 and make it 1/3, make my numbers a little bit smaller. Now that's something that might come up in quadratic formula that might not come up in vertex form because your numbers start simpler in vertex form because you've already done all of those calculations to get there, especially with a leading coefficient bigger than 1. That's really what got us to here that it might not have if it wasn't. Good question. Thank you. Yay, questions. I want questions. Other questions. Are we all good? Otherwise, number 2? Sweet. Okay. So that was just 1 and 2. I just wanted to make sure you had that skill. And then 3, 4, and 5 was factor completely. Okay. And I really don't have to say factor completely. I'm never going to ask you to factor incompletely. But these are all kind of that new style of factoring that we figured out last Friday. Similar to the difference of perfect squares, we have some in difference of perfect cubes, right? With that a squared, ab, b squared. And then what do the signs spell out? That's how you remember the signs. Same, opposite, always positive. So the original was subtraction, so same, opposite, always positive. Oh, addition, same, opposite, always positive, okay? And I find it really helpful with something like 3 and 4 to write it. I mean, x cubed minus 1 is pretty obviously x cubed minus 1 cubed, so maybe you don't need that inside step there, but maybe you do. It's very helpful. But with something like 4, it can be really helpful to rewrite 8x cubed as 2x cubed and 125 as 5 cubed, because then it's 2x, 5, 2x quantity squared, so I got to square the 2 and the x, and then 2x times 5, so 10x, and then 5 squared. Same, opposite, always positive. But what's the first kind of factoring we should always look for if it's there? If there's something that you can factor out first, before you ever get to quadratic trinomials or difference of squares or sum and difference of perfect cubes or anything like that, what's the first kind of factoring to always check for? And that's what happened in 5. We have a greatest common factor, right? Between 3x to the 10th and negative 24x to the 4th, you've got a 3 as a constant in common. And between x to the 10th and x to the 4th, I've got an x to the 4th in common that I can pull out. And so that right there, that 3x to the 4th, that is your greatest common factor. So pull that out first and see what's left. Well, take a 3x to the 4th out of this. You just have x to the 6th left behind, because when you multiply variables together, you add their exponents. So that's why the 4 and the 6 get me to 10. And when I take out 3x to the 4th of negative 24x to the 4th, I've taken the 3 out, so I just have the 8 left. But I've taken all of the x to the 4th, so there's no x's left. But then look inside and see what's left. If it's factorable, then keep going. Okay, I've got the difference of two things, so I'm looking for either the difference of squares or the difference of cubes. Well, 8's not a perfect square, so I don't want to write like plus or minus the square root of 8. That's when I factor, I try to want to avoid irrational numbers. But if I can write it as the difference of cubes, then I can factor it. And because 8 is 2 cubed, that one's pretty easy. But if I want to write x to the 6th as something cubed, I need to figure out what exponent should go with that. And when you raise a base to a higher base to a power to a higher power, these two numbers would get multiplied together. So if I'm going to say, okay, this is x to the something cubed, well, I need to figure out what cubed is 6. Like what times 3 is 6, and so that's x squared. And so your base is x squared for the first one, and your other base is 2. So x squared, 2, x squared squared, so x to the 4th, 2x squared, and then 2 squared. Cool. Sweet. All right. And then last, just wanted to talk about some end behavior. Just wanted to make sure that we can figure out what direction our arrows are going to be pointing from our lesson that we talked about on Tuesday, finally getting into 2.2, some new stuff. Okay. And so I wrote down the functions, and then on the right, I just wrote down the only things that matter. what's the degree and what's the sign of the leading coefficient, which of course I just called a sub n. So my degree was odd for this one because the biggest power is 3. And the leading coefficient is 1, so it's positive. And so remember, the leading coefficient is what tells you what the right arrow is doing. If the leading coefficient is positive, your right arrow goes up in the positive direction. If the leading coefficient is negative, then your right arrow goes down. And so I'm always going to be able to figure out my right arrow first. Then I figure out the left arrow based on the degree. So I know I kind of wrote these degree first and then leading coefficient, but you really should be thinking about leading coefficient first and then using the degree to decide, should it go in the same direction or opposite? Same direction or opposite. So positive leading coefficient, so I'm going up this way. Degree is odd, so I'm going down that way. So you can say down, up, or you can just draw those little arrows like I do. But look, I went down and out, and then up and out, not just straight up and down, okay? For 7, leading coefficient was negative, so I know my right arrow is down. Degree is even, so I know that they're the same. Down, down. For 8, leading coefficient is positive, so right arrow, up. Degree is even, so same. So up and up. And leading coefficient is negative for number 9, so down. Degree is odd, so opposite. Up, down. Good. Okay, cool. All right, let's pick up right where we left off on Tuesday. You disappear, but you come with me. Somebody unmute yourself at home and tell me if this camera quality is better than it has been in the past.
It's so much better, Rosie.
Oh, that's amazing. I'm so happy. Okay, good. I want to get you close.
Probably is better.
Good. I'm so glad to hear that. Okay, good. All right, let's pick up right where we left off and see if we can get some headway into 2.2. I've got some ideas for what I want to try to accomplish between now. So we got Thursday. Sorry. We'll see how far we get. I don't know what we'll do tomorrow. But then we got Tuesday, Thursday. My guess, oh man, I don't know. So I trust you guys to do what's right at home, but Algebra 2 let me down last week, and they cheated on their take-home quiz. They were sharing answers, and it ended up on Snapchat. Can I trust you? Okay, good. Here we go. What was the function that we finished up with? You guys have it in front of you? I think it was example 4 from the textbook itself. Man, this is so low, though. What was that last equation that we were messing around with? Like x cubed? Yeah. X cubed minus x squared minus 2x. And we just wanted to do a couple things. 1, talk about the end behavior, but 2, finally get to the x-intercepts with some higher degree polynomials. So what would be, let's talk about end behavior first. How about that? End behavior. What's the sign of your leading coefficient? Positive. And so what that tells me is that my right arrow is going up. Cool. So that's one thing. And then what's the degree? What's the parity of the degree, even versus odd? Largest exponent is a 3, so that's odd. So I know that I've got opposite directions. So I know that I've got up on one side and down on the other. Okay, cool. The other thing that I think we talked about, I'm going to come over here, I guess, to do it, is we mentioned what the y-intercept would be. Because if we're going to sketch the graphs of these, because 2.2, graphs of polynomials of higher degree, it was just that constant at the end, right? Whatever a sub 0 is. So, all right, 0 comma a sub 0, what's the constant at the end of this function that doesn't have an x attached to it? 0. All right, so there's a plus 0 sitting there. Now, if that was a +1 or a -7 or a +12 or whatever it is, then okay, then there's our y-intercept. But if you don't have a term that doesn't have an x, you have a +0 sitting there. Okay, cool. Now, the good stuff, finding whatever x-intercepts we've got. So what should we take this function and set it equal to? 0 question mark? Yeah, good. Is there one x in this problem, or are there more than one? We got different degree terms in there, so we can't solve for it directly. So what do we need to do to solve? And we always start with the GCF. Good. So GCF first. Is there a greatest common factor? Take it out. X squared minus x minus 2 left behind. And when you get to the next kind of factoring, it's not like there's one that's better than the other. We just have to pick what we've got. And what we saw was that we have a quadratic inside. It's got 3 terms, so we call it a trinomial. And that's where we do our factoring, right? What adds to b and multiplies to whatever a times c is. Okay, so what 2 numbers add to -1 and multiply to -2? And because your leading coefficient is 0, -2, +1, you can factor it right away. You don't have to wait and go through the box or go through factoring by grouping. If it's got a leading coefficient of 1, life is so much easier. Now, how many unique factors are there, including that GCF? So that means you've got 3 x-intercepts, right? I've got one for this one for this one, and one for that one. So we'll set each one equal to 0 and solve. So if x equals 0, done. Well, we knew that one. I had the origin as a point, because that's the y-intercept. So I expected that one. And we've got 2, and we've got -1. And all 3 of these are points that we want to plot and sketch. And that's what I want to do. Okay, I want to finally get to sketching the graphs of these. I think we started. If we didn't, let's do it now. Let's draw a set of axes. Now, I want to talk about when we sketch stuff here, polynomials and rationals. So all of chapter 2, what's the bare minimum that we need to design a graph that does enough? Well, I just drew the axes on there. What do we need on those axes for sure? Numbers. Yeah, we need a scale, right? And so I want to make sure that my scale makes sense for what I've got. I know I've got to plot the point 0, 2, and -1. And I just want to give myself a little bit of space on either side. I don't need to go out to -10 and +10. I don't need it. And so when I design this graph, I can make it look however I want. Let's give ourselves at least 2 boxes on either side of the number as far to the left and as far to the right. So my number that's as far left as possible is -1. So I know I have to go out to at least -3. And I've got to go at least as far as 2 here on the right, because that's my biggest x value. So I better make sure that I go 1, 2, 3, 4. Now I am sketching this by hand very informally. You can always do it better than this. You can break out the ruler, you can break out the graph paper and do it nicer. To make things look really, really nice, you want to make sure that your tick marks are as evenly separated as you can. And let's give it a scale. Now, if you want to write 1, 2, 3, 4, -1, -2, -3, go for it. But the moment you give me what 1 box is worth, now I'm good. That is the minimum that I need for my scale here. What's the only y value point that we've mentioned so far? And that just happens to be the y-intercept, right? When we graph polynomial functions, when we sketch them, the only y value that we're going to care about in pre-calc compared to calculus, in pre-calc is the y-intercept. I don't need you to go 1, 2, 3, 4, 5, 6, -1, -2, -3, -4. If your y-intercept was 12, just write that. If your y-intercept was 3,000, just write that. I only need one y value point. Our y value point is this one. So right now, we don't need it. Okay? What else does this graph need to get a little bit more filled out? Before we even plot points and connect it. Arrows. Yeah, you gotta tell me this graph goes on forever. Throw some arrows on the end of your axes. There's only one more thing. So we gotta scale. Before we even plot points. Labels. I gotta know what graph we're looking at. We're looking at x and not necessarily just any y, but g of x. Label your y-axis with the name of your function. Okay, so we need those three things. I need labels, I need scales, and I need my arrows. Now all I have to do is plot my x-intercepts and draw my arrows. So when we sketch graphs, we've got some things that we want to make sure we do, right? Create a set of axes that do what we need. Labels, scales, and arrows. Okay, so I think you can remember that. Okay, next we will plot our x and y intercepts. And those are the only points we're going to need when we sketch. Okay. I like to switch colors between my axes and the graph that I'm doing. That's just me. Okay, so 0, 2, and -1. Now I draw the arrows. And if those are the only x-intercepts, I'm going to make sure that my end behavior matches what I expect. When I draw my x-intercepts, and I've drawn them all, what I know is that this graph is never going to come back to the x-axis. And so if my points exist in this, so everybody at home, if my points exist in this space right here, should my arrows go in this space on the inside? No, it's got to go in the space on the outside. And so when I draw my arrows, I go to the left x-intercept and the one on the right, and I make sure that my arrows exist outside. And I know what they're supposed to look like. Here's my one on the left. I know that my arrow needs to be down and out. So I come down here, and I draw that arrow. On the outside of your furthest left x-intercept, give yourself some space, because we don't know quite what's happening yet near the x-axis. Okay, and the one on the right, I go to the right one, I go out like a box or so, and I point it up and out. Then we're going to connect from left to right. Start at your left arrow, connect to your x-intercepts, your y-intercept. And remember, functions that are polynomials are continuous. There's no gaps, there's no breaks, there's no holes. And they're smooth and rounded. Come up, hit this x-intercept. I got to go through it, right? But now what do I have to do? How am I going to get back to this one? I have to turn, nice. And I have to do it smoothly. We don't know where that maximum is. In pre-calc, we don't care. We just have to turn somewhere. Usually I turn about in the middle, somewhere in between. I go like that. And I'll cut right through it, and we'll talk about when we'll do something different. Okay, so there I go. I cut through this first x-intercept. I got to turn somewhere, so I'll turn. I'll come back down. Okay, and now I got to get back to the x-axis. What should I do? I got to turn somewhere, but I'm going to turn smoothly. Nice and rounded, and it's somewhere in the middle. And I'll cut right through it. Do I ever have to come back to the x-axis once I've gone through x equals 2? Connect to your arrow. Check this out. Go to your calculator, and let's see how we did. X cubed minus x squared minus 2x minus x squared, delete u, minus 2x. It's pretty good. Doesn't that look like that? That's pretty good, right? And remember, the calculator is not going to draw arrows. We have to. Awesome. Good? Cool. All right. Now, let's see what happens if... So that was this one. That was this one. All right, find all the real zeros, but we did the graphing too. Let's try the next one. Let's try this next one. Okay. Now I know that there's 3 there. I'm just going to freeze this because I want to bring it. I want to bring everybody back with me. But we're just going to do the negative 2x to the 4th plus the 2x squared. We'll get to example 8 and 9 here in a little bit. Okay. So I'm going to go over there. So I want to leave that up for us. I'm going to bring you guys with me at home. Now, if you are at home, I have to stop sharing my screen for you to be able to see as well, I guess. I mean, I guess you could pin it if you really wanted to. You could pin my separate video. Sorry, I know you're staring at me right now. Okay, cool. Something like that. Okay. All right, let's do it. 50-50 shot. Yes. Nice. All right, folks at home, let me know if you need me to fix anything with the screen. Otherwise, here we go. All right, so example 5 says find all the real zeros. I know it says and the relative extrema. We can't do that without a calculator. So I'm not going to worry about that part. What I really just want to do is the stuff that we've been doing. Negative 2x to the 4th plus 2x squared. Let's do end behavior. Let's find the y-intercept, and let's find the x-intercepts, and then we will sketch it. Okay. All right, so end behavior first. Sign of your leading coefficient. Negative. So what does that tell you? What does that tell you? The right arrow is down. The leading coefficient only tells you about what's happening when x goes to infinity. All right, that's really what's happening. Okay, so the arrow is going down. What that means is that y is going to negative infinity. So when x goes to infinity, y goes to negative infinity. Cool. All right. What's the other thing that matters for us for end behavior? Even or odd, right? And it's the degree. What's our degree? It's 4, right? Yeah, largest exponent is 4, so that's even. So what does that tell you? Same direction. So if the right arrow is going down, the left arrow is also going down. So I know that my end behavior is down, down. Now, you don't have to write that stuff down, but that's how you want to think about it. If you just say end behavior, down, down, cool. I'm good with that. Okay, where is your y-intercept? Yeah, there's a plus 0 here, right? So 0. Okay, what about x-intercepts? How do we find those? What do we need to do first before we bother factoring? Set it equal to 0, then we'll start factoring. Good. So I want to see this first. I want to see that step where you set this thing equal to 0, because then I know that we're trying to solve for something, and we'll do it by factoring. Okay, first kind of factoring we should always look for GCF. So what should we pull out? 2x squared. If you have a negative leading coefficient, take that out with it. Okay. What's left inside should have a positive leading coefficient no matter what. So if you've got a positive, take it a positive. If you have a negative leading coefficient, take out that negative. Okay. What's left behind? X squared, because this would multiply back to here. And then we took out everything, but we took out a negative, so the sign has to change. Okay, first step of factoring, done. Is there more that we can do? Well, is what's left inside a quadratic trinomial? No, I don't have 3 terms. But what is that inside, that x squared minus 1? It's the difference of perfect squares, right? The difference of 2 squares, which I call dots. Okay, we've got dots. There we go. And so let's keep factoring. Don't stop. How is this going to factor? Thank you. Okay, and the whole idea of factoring is to break it apart. Solve and see what we get. So we take the first one, set it equal to 0. Take the second one, set it equal to 0. Take the third one, set it equal to 0, and we see what we get. How many x's are in each of these factors? Just one, right? I know the degree of this one happens to be a 2, right? But solving for that x-intercept is still just solving that equation. Okay, divide both sides by -2. What's 0 divided by -2? Okay, and then I take the square root. What's the square root of 0? So we get plus or minus 0. Do I need plus or minus? No, it's just 0. Of course it is. If your y-intercept is 0, we better get an x-intercept of 0 as well. And then, of course, -1 and 1. 1, 2, 3 x-intercepts. Okay, so now let's do the sketch. We got all we needed. Now let's sketch. Okay, create a set of axes. Ta-da! What do we need to add? Scale. Now, I just want to look at my numbers. I just want to see what matters. Okay, I got to go as far left as -1 and as far right as 1. I just really need a couple boxes, a couple tick marks on either side. So I'll go out to like -3 and 3 instead of -1 and 1. But you got to tell me what that scale is. Put a 1 in that first box, or put a 2 in the first box, or a 10 in the first box. Whatever you want every box to be worth, then put that there. If you want to put 1, 2, 3, -1, -2, -3, go for it. But you don't have to. Just 1 is good enough. Do I need a scale for the y-axis? All I need to do is plot the y-intercept. Where is it? Well, it's at 0, so I'm good. I don't have to worry about that. Okay, got scale. What else do I need? Arrows. Throw some arrows on the end of your axes. And labels. X and the name of the function f of x. Okay, cool. Now, changing colors, because now I'm going to do the graphing. Okay, create a set of axes, done. Plot your x and y-intercepts. Okay, so 0, -1, and +1. Okay, I got my 3 points that mattered, right? I got my y-intercept that kind of overlaps because they're the same. Okay, create a set of axes, done. Plot x and y-intercepts, done. Arrows and behavior. Okay, I did that. I want to go down and down. And it just has to happen on the outside. Just kind of go a box or so past your last x-intercept on the left. So we'll go down this way, and we'll go down that way. And you can make them relatively small. You can always erase them if it doesn't flow nicely with the way you connect the graph. It's just a place for you to start, because the last thing we're going to do is connect from left to right. And if you've got your arrows already there, then you know how to connect them. Okay, and let's just cut through, right? So let's do it. So I cut through this one. I go up. What do I have to do? Well, I got to turn somewhere. So about in the middle, I'll do it. So I'll turn, I'll go down. Cool. I got to turn somewhere, and I got to go up and... Uh-oh. What happened? Is our end behavior right? Leading coefficient is negative. Degrees even. Okay. We didn't miss any x-intercepts. Something got screwed up when we tried to connect it. Okay, time to back up. There's something that's different about this function compared to that one. What is the degree? At home, they're probably getting nauseous. Sorry. I just want you to see. What is the degree of every factor in this function separately? What's the exponent right here attached to x? What's the exponent attached right here? Which is really just like right here. Yeah. What's the exponent attached to this one? And so take a look at how each of these cross through their x-intercepts. Like a line, right? If you just zoomed into those spots, those all look linear, right? Okay. What's the degree of this factor? The degree of this one? The one on the outside is what I care about. One on the outside. And so your degree of your factor is going to influence the way it intersects the x-intercepts. Okay, when it's degree 1, it hits it like a line. So, okay, here I am, x equals -1. The degree of that factor is 1. So when I connect this graph and I cut right through this, I better do it like a line would. Okay? Now I got to take a turn. I have to take a turn. I got to come back somehow. But what's the degree of the factor that got you to that x-intercept? And so if it's x squared, what do those graphs look like? That's how it's going to hit the x-axis. My degree of this x-intercept was a 2, which means when I intersect the x-intercept, I have to do it like a parabola. Now I got to take a turn and come back. What's the degree of the factor that got you to x equals 1? So I got to hit it like a line. And that's what that graph looks like. If you look at it in the calculator, it's exactly the same. Okay, have you seen that before? Okay, good. So, do you remember what that's called? How the degree of your factor influences the way you intersect the x-axis. It's called the multiplicity of the zeros. How many times, multiples, do we see that factor? Really, this is just x twice. This is x plus 1 once. This is x minus 1 once. Okay? And so what we have is a scenario where how should I say this? The behavior of the function at the roots, zeros, x-intercepts, all relatively the same thing. I'm just going to use different words here to get used to them. The behavior of the function at the roots depends on the degree of each factor. Okay? If we compare degree to behavior, and that's so light, I need a brighter color. If your degree is 1 for that factor, it's going to cut through it like a line would. Now, it might go up or it might go down, but it is going to be in that space, it's going to look linear. Just like this one and that one and all three of those. But if your degree is 2, the behavior at that spot is going to look quadratic. I'm going to put parabolic because we're talking about the shape, not the function. What do cubics look like? I love that. All right. But that turn that it takes right there doesn't go up, down, and then back up. It's going to happen flat. Because if you think about what x cubed looks like, it doesn't actually ever take a turn back up and then down and back up. This function is always increasing. And so it is going to look cubic, either going up or going down. Okay. So let's do one more. And then we'll add 4s and 5s and 6s and 7s probably tomorrow. I think we can get ourselves to here. And I'm glad that you've seen this before. Have you seen this multiplicity of the zeros action where the graph takes turns and stuff? Okay, cool. So I just want to make sure that we've got that before we get all crazy, because then we're going to look at functions that are this big with like this many factors and make sure you can do the whole thing. But if this is old news to you, good. That makes life that much easier. Okay, cool. Let's finish this one up. We'll do example number 8. And we'll call it a day right there. Okay, so f of x. 3x to the 4th minus 4x to the 3rd. And let's do it all. And behavior, y-intercept, and x-intercepts. Again, folks at home, make sure you log in to Infinite Campus and take your attendance. Okay, first, what's a great place to start? At the end. Up, up, down, or down, down. These are the only things that matter. Positive leading coefficient, right arrow is going up. Even degree, same. Up, up. Y-intercept, 0, comma. There we go. Okay, good. Nice. All right, x-intercepts. What should we set this thing equal to? 0. And what's the first kind of factoring we should always do? Because we've got different powers of x. GCF. So take out whatever's in common. Between 3 and 4, is there any number, any constant we can take out? And we won't bother taking out fractions if there's no fractions to start with. If there were fractions buried in here, I might consider it. Like, take a look at example 9. Look at your coefficient of x there, 9/2. I'm going to take out a constant that is a fraction so that what's left inside will be an integer. But here, I don't have any fractions to start with, and I don't have anything in common. So we'll just take out a power of x that's big enough. 4 x is in the first one, 3 in the second one. All right, exponents. How many can I take from both without taking too many? 3, right? So if I take 4 from something that has 3, then I'm getting to negatives. That's no good. So let's take out an x cubed. Okay, what's left? Good. 3x minus 4. And the idea is to separate them. X cubed equals 0, and 3x minus 4 equals 0. Take the cube root of both sides. Cube root of 0 is still 0. Add 4, divide by 3, 4/3. Arrows, labels, f of x, and a scale. Now, if I make every box go by 1s, am I going to be able to perfectly plot the number 4/3? So what could we make every box worth so that we hit 4/3? What could we make our scale so that I land on a tick mark at 4/3? I got to bring these people back. We can make it a third. And then we just have to go 4 boxes to get there. What else would work? 2/3, because then we go 2 boxes and then I get there. or the number. Make it the number. Because I don't have to worry about like also hitting 1 or -2 or 1/5 or something else. So you have some choice here as to what works for you. I'm going to go with 4/3. Make this thing right there 4/3. Who cares? Okay. And now I just need a box or two past that to make sure I can draw some arrows. I don't have to create a y scale because my y-intercept is 0. If it was 10, I would just go up a little bit, make it 10. If it was -30, I'd go down a little bit, make it -30. I don't have to worry about that. Our x and y scale can be different. Okay, axis done. Plot my x and y intercepts. 0 and 4/3. Now I draw the arrows on the outside. Up, up. And now I connect them from left to right. But what is the degree of the factor that got me to x equals 0? The exponent that's attached to it. So this factor got me to this equation that got me to that solution. That's my x-intercept at 0. I have to check the multiplicity at that 0. So when I connect from left to right, I have to consider the multiplicity of each 0, of each root, of each x-intercept. And so if my multiplicity is 3, that means I have to cut through it like a cubic. I have to choose either this one or this one, depending on which way I'm going while I'm going down. So I'm going to get really close to the x-axis. I'm going to turn, flatten out, and head down. Now I've got to take a turn and head back up. Where do I do it? About in the middle somewhere. Whatever's comfortable, whatever flows nicely, it's got to be smooth and rounded. Now, before I get to that x-intercept, I stop. I pause. I pick up my pen for a second, and I say, okay, what's the multiplicity at this 0? Well, it's the degree of this factor that got me there. What's the largest exponent? So I got to hit it like a line, which means I just cut right through it. I'm done with my x-intercepts, and away I go. And just for fun, let's head back so you can see it, and then we're done. No bells, at least for the first half of the day. There might be more bells later. Here, I'm going to turn it towards the people. Hey, look, it's you. So you can see. Check this out. And then we'll head out. Let me present so that everybody at home can see, and then you guys are good to go. So first, the last one before that, -2x to the 4th plus 2x squared, and 3x to the 4th minus 4x to the 3rd. Let's turn this one off for a quick second. Right? We had to take that turn. Let me get in a little closer. I'll zoom decimal, right? That multiplicity right at 0. And then we'll turn this one on. We'll turn this one off. Let's get a little closer. You see that action at that x cubed. Yeah. All right, check Canvas for a little, I don't know. I don't know yet. I'll let you know. Maybe we'll just show up tomorrow live and we'll just keep going. That's what I'm thinking. Thanks, everybody. Have a good day. Thanks, everybody at home. You guys are good to go. Check Canvas. Any questions?
Thank you.
You're welcome. See ya.
Thanks.
Adios.
Bye.
Thank you.
Thank
You're welcome. You're welcome. See you guys.
Thanks.
See ya.